Okay, so in this video I want to talk about some surfaces that are not constant surfaces, but I've given you some equations for some familiar surfaces in rectangular coordinates, and I want to just convert those over to cylindrical coordinates. Okay, so the unit sphere I know is just x squared plus y squared plus z squared equals 1. Now when I convert to cylindrical, the z's just stay exactly as they are, and I'm always thrilled when I see an x squared plus y squared, because that's just r squared. So this becomes r squared plus z squared equals 1. Similarly, this paraboloid, z equals x squared plus y squared, is just z equals r squared. Nice. Now here, I'm telling you that this is a half cone. Hopefully that's a familiar surface, so hopefully you're starting to recognize it, but let's remember how we could see that that's a half cone. If I square both sides, I'm going to get z squared is x squared plus y squared, but I need to record that z is non-negative because that restriction is implied by that original equation. Okay. Now, if I look in the xz plane, I'm getting a degenerate hyperbola, which is just intersecting lines. Same thing in the yz plane. In the xy plane, where z would be 0, I'd have just a single point, but if I were to move up, I'd be getting a circle. Okay. So we're just getting a half cone that's opening up, like so. Now when I convert to cylindrical, I have to be careful. If I'm just working in cylindrical coordinates with no restrictions on r, this would become z equals the square root of r squared, which would be the absolute value of r. Almost always when we're going to encounter this, it's going to be in the context of integration, when we're going to make the choice that we're only going to use non-negative r values. And if that's the case, then I can say that means just z is equal to r. Okay. All right, let's take a look at another surface. Let's say I had x squared minus y squared plus z squared is equal to 1. This is going to be a hyperboloid in one sheet. I can see in the xy plane I'm getting a hyperbola. In the yz plane I'm getting a hyperbola. And in the xz plane I'm just getting a circle. So this is going to be a hyperboloid in one sheet with circular cross sections. And it's going to it's going to be centered around the y-axis. So it would look something like so. Okay. Now I know my z's are going to just stay as z's. Here I'm no longer adding x squared plus y squared, so I'm going to have to just convert those individually. So x squared becomes r squared cosine squared theta, minus y squared is r squared sine squared theta, plus z squared is equal to 1. That is a perfectly acceptable answer if you are asked to convert that surface into cylindrical coordinates. But there is some simplification I can do that might make it easier for me to work with that surface. If I factor out my r squared, notice I get cosine squared theta minus sine squared theta, and then still plus the z squared equals 1. That's my double angle formula for cosine. So this is r squared cosine of 2 theta plus z squared, I'm sorry, not plus 1, equals 1. Okay. All right, so I can convert my equations to cylindrical coordinates. So you'll be doing some of that in the homework. Most of what we want to do, of course, is integrate. So, if I have the triple integral over e of f of x, y, z dv, and I want to write that in cylindrical coordinates, I know how I'm going to switch the integrand. X is just going to become r cosine theta, y is going to become r sine theta, z is going to stay z. I need to think about what dv becomes. Okay. Now, if we think about how we would set up an integral, we always go through this process of chop, approximate, add, and take a limit. Okay. I want to just look in particular at that chopping step. In rectangular coordinates, we would chop things up into rectangular boxes. Rectangular boxes are just regions that are bounded by 4 constant surfaces. x equals constant is the left boundary. Sorry, it's the back boundary. X is constant is the front boundary. Y being constants are the left and right boundaries. Z being constant are the top and bottom boundaries. Okay. If I'm going to chop things and I'm working in cylindrical coordinates, I would want to chop things using two constant R curve surfaces, R equals R1 and R equals R2. So that's going to give me two cylinders. Theta equals theta 1 and theta equals theta 2. That's going to give me two half planes. Now remember, it's half planes because if we're integrating, we are making an executive decision that we are going to use R values that are non-negative. Okay. And then I would have Z equals Z1 and Z equals Z2. That would be two planes. If I look at the region that's bounded by these six constant surfaces, that region would be called a cylindrical wedge. So we're chopping into cylindrical wedges. And essentially, what I'm getting is these four boundary curves would just describe a polar rectangle in the XY plane, and then I'm doing a vertical extrusion of that. So, I'm going to basically be getting something, you know what, I can draw that better. So I would have some polar rectangle in the XY plane, and then I'm just doing a vertical extrusion of that. And there's my cylindrical wedge. Okay. So the volume of this is the area of the base times the height. But we figured out what the area of a polar rectangle is. Okay. So essentially my delta V here would be approximately an R value, where I'd have some representative R value, times delta R, delta theta, delta Z. And actually, I know it's exactly, if I were to choose the average radius, I'll just put R star here. If I were to pick the average radius here, that would give me the exact volume. This would give me the approximate volume. Okay. So what that tells me is that dV in rectangular coordinates, I know is just dx, dy, dz, in whatever order is appropriate. dV in cylindrical coordinates is going to become r, dr, well, all right, dz, dr, d theta, just because that's the order we're usually going to set things up in, although of course we can Frobenize and do things in other orders if we like. Okay. That shouldn't come as a big surprise, because essentially using cylindrical coordinates is equivalent to using polar coordinates. So there's my dA, there's my dA, and then there's my dz. Okay. So just like with when we integrate in polar coordinates, we're going to be getting an extra factor of r when we set up our integrals. Okay. All right, so that's the theory behind it. In the next video, we'll actually do an integral in cylindrical coordinates.